Apple just released an interesting research paper last week which talks about the illusion of thinking, which is about understanding the strength and limitation of reasoning models. And what they are saying is that large reasoning models don't actually think, right? And they have identified three performance regimes: low complexity tasks where standard models surprisingly outperform large reasoning models, your standard LLM; medium complexity tasks where additional thinking in large reasoning models demonstrates an advantage; and then there are higher complexity tasks where both models experience complete collapse. So reasoning models are not able to solve these high complexity tasks. And what they are saying is that this means that large reasoning models cannot generalize well to solve problems. Now, the timing of this paper is a little bit circumspect because WWDC 25 just happened yesterday and they did not really touch too much about AI. Whereas in WWDC 24, the whole point was about Apple Intelligence, and Apple is currently one of the laggards in AI. Their Apple Intelligence is nowhere close to the other, LLMs or models from the other labs. It's a spectacular failure, I'll put it like that, right? But this is an interesting paper. So, what is a large reasoning model? A regular large language model may only provide a short answer for a question, whereas reasoning models typically include intermediate steps that reveal part of the thought process. So, large reasoning models have some kind of a thought process. Okay, so most LLMs branded as reasoning models today include a thought or thinking process as part of their response. Whether and how an LLM actually thinks is a separate discussion. So this is an interesting definition of reasoning models. Okay, so this is a blog post from Sebastian Rashka. I also have an explainer video where I explain what are these reasoning LLMs based on the blog post and how you can train reasoning LLMs. So you can check out this video as well. Now let's go back to the paper, right? So what are they saying over here? So your current large language models or recent generation of frontier language models have introduced large reasoning models that generate detailed thinking process before providing answers. So how have they evaluated this particular large reasoning models? Current evaluations focus on established mathematical and coding benchmarks, emphasizing final answer accuracy. This evaluation paradigm suffers from data contamination. Okay, so since they are evaluating on benchmarks, there is a good chance that they have already been trained on some of these benchmarks. And this evaluation paradigm does not provide insights into the reasoning trace's structure and quality. What they've done in this particular work is that with the help of controllable puzzle environments that allow precise manipulation of compositional complexity while maintaining consistent logical structure, they are doing analysis of not only the final answers of these large reasoning models on these kind of problems, but also the internal reasoning traces, which kind of offers insights into how these large reasoning models think. So what they are saying is that through extensive experimentation across diverse puzzles, they show that frontier large reasoning models face a complete accuracy collapse beyond certain complexities. They exhibit a counterintuitive scaling limit. Their reasoning effort increases with the problem complexity up to a point, then declines despite having an adequate token budget. So by comparing large reasoning models with their standard LLM counterparts under equivalent inference compute, they identify three performance regimes: low complexity tasks where standard models surprisingly outperform large reasoning models; medium complexity tasks where additional thinking in large reasoning models demonstrates advantage; and high complexity tasks where both models experience complete collapse. This is something which I've seen practically as well. I've seen some low complexity tasks where your non-thinking LLM performs really fast and your thinking LLM kind of goes into a loop of overthinking. It keeps generating the same thing. So these were simple mathematical calculation where I have practically experienced this, where I see that your standard LLM gives a direct answer outright very fast, whereas your thinking LLM goes into kind of overthinking. It tries to verify again and again whether I'm solving the problem correctly, wasting compute. So this is something which I've practically observed as well. So what they are saying is that large reasoning models have limitations in exact computation. So if you provide explicit algorithm and ask it to solve some puzzle, still it is not able to do it. So this is an interesting work. All they have provided is a problem with reasoning models. They have not provided a solution in this particular paper with the expectation that people will try to solve this problem in the future. So now what they are saying is that, right, at low complexity, non-thinking models are more accurate and token efficient, as shown in this particular graphs over here, right? For as complexity increases, reasoning models outperform but require more tokens. So that is a medium complexity. And when you have a high complexity task, both the models kind of fail, right? So this is what they are saying over here. So how did they do this? They compared various state-of-art large reasoning models like O3 Mini, DeepSeek R1, Claude 3.7, Sonnet Thinking. And what they're saying that these models still fail to develop generalizable problem-solving capabilities with accuracy ultimately collapse to zero beyond certain complexity across different environments. They say that there exists a scaling limit in the large reasoning models' reasoning effort with respect to problem complexity, evidenced by the counterintuitive decreasing trend in the thinking tokens after a complexity point. So the assumption is that as the problem becomes complex, the large reasoning model should use more thinking tokens. But what is happening over here is that the thinking tokens are in a decreasing trend when you have more complex problems. So this is a counterintuitive thing which is happening, right? And what they are saying is that, with a deterministic puzzle simulator, they are able to evaluate, beyond the current paradigm of final accuracy. They are extending it to, understanding intermediate solution of thinking traces to see how solutions emerge. And, when do they emerge in this process of thinking? So this is what they are talking about over here. So what is there? How are they evaluating this? So they have 4 problems over here, puzzle problems. One is Tower of Hanoi, checkers jumping, river crossing, and block words. Let's look into each of it. Right now, Towers of Hanoi is a puzzle featuring 3 pegs and n discs of different size stacked on the first peg in size order, and you have to use the intermediate peg, and then you can move from the top one disc at a time, and you have to actually the target state is this, where you have moved all the discs from the first peg to the third peg. So there are some valid moves over here, right? And what they're saying is that the difficulty in this task can be controlled by the number of initial discs, as the minimum number of required moves with n initial discs will be 2 to the power of n minus 1. Okay, so they do not grade for optimality of final solution, only measuring the correctness of each move and reaching the target state. So the goal over here is to transfer all discs from the first peg to the third peg. Valid move includes moving only one disc at a time, taking only the top disc from a peg and never placing a larger disc on the top of a smaller one. So these are some constraints for Tower of Hanoi. So here, how are you scaling the complexity of the task? You are scaling it by increasing the number of discs in the initial state, right? So using that, you can actually increase the number complexity, because depending upon if there are n initial discs, you require 2 to the power of n minus 1 moves for solving this problem. The second is a checker jumping problem. Okay, so it is a one-dimensional puzzle arranging red checkers, blue checkers, and a single empty space in between them in a straight line. Okay, so that is what it needs to be done over here. So the complexity of this task can be controlled by the number of checkers. With 2n checkers, the minimum number of moves required will be n plus 1 square minus 1. So depending upon the number of checkers over here, if the number of checkers are increasing, again the solution space also increases. It becomes more and more complex. Okay, so valid moves include sliding a checker into an adjacent empty space or jumping over exactly one checker of the opposite color to land in an empty space. No checker can move backward in the puzzle process. The next is river crossing, is a constraint satisfaction planning puzzle involving n actors and corresponding n agents who must cross a river using a boat. The goal is to transport all 2n individuals from the left bank to the right bank. So this is the river crossing. How do you cross agents from one side to the other side, right? So here the complexity of this task can be controlled by the number of actor-agent pairs present. For n is equal to 2, n is equal to 3, we use boat capacity of k is equal to 2, and for larger number of pairs we use k is equal to 3. So the idea over here is that you have a boat, you have a person with some animals or something like that over here, you have to cross them to other side. Similarly from other side to this side. So how do you do it? Whereas there is some capacity constraint in the boat as well, right? The last one is blocks world. It's a block stacking puzzle requiring rearrangement of blocks from an initial configuration into a specified goal configuration. The objective is to find minimum number of moves needed for this transformation. Again, valid moves are restricted to the topmost block of any stack, which can be either placed on an empty stack or on top of another stack. The complexity in this task can be controlled by the number of blocks present. So what they have done is that they have 4 puzzle environments. where they can change the complexity in each of this puzzle environment from very low complexity to high complexity. And for each of them, they are going to ask the reasoning LLM and the non-reasoning LLM to generate the output. And then they're going to evaluate how accurately it is able to generate the output. They're also going to look at intermediate traces in thinking to find out how the model has reached the output. So this is what they have done, right? And what they have found out over here is that, this is the accuracy of thinking models, Claude 3.7 Sonnet with thinking DeepSeek versus their non-thinking counterparts over here in the Tower of Hanoi. Okay. So if you see over here in the graph, after some point of time, the accuracy kind of fails when complexity increases in the number of disks in the Tower of Hanoi. Across all the models, as complexity increases, you see that the model kinds of fails, right? Thinking or non-thinking doesn't matter. It kind of fails over here after some complexity. Okay, but what they're saying is that when you are having low complexity, for example, over here, when the number of towers is equal to, say, number of disks in Tower of Hanoi is equal to, say, less than 3 or something like that, the thinking model, the non-thinking model also does good over here, slightly better than maybe the thinking model in accuracy. But after some time, between this, say, towers is equal to 3 to 8, you will see, or 3 to 10 or 8 over 10 over here, you will see that the thinking model performs better, right? And after this 10 number of disks, both models are not performing well, right? They kind of reach a zero accuracy. That is their thing. Now they're asking, like, why does this happen? Okay. So the question is that they're asking, like, why does this happen? So what they did was they started looking at the thoughts of reasoning models. They extract and analyze the intermediate solutions explored within the thoughts of a model with the help of puzzle simulators. They examine the patterns and characteristics of this intermediate solution, their correctness relative to their sequential position in the reasoning process, and how these patterns evolve with increasing problem complexity. So when it is trying to solve the problem, the LRM, it kind of gives this reasoning traces, right? In that trace, they are trying to find out where is the correct solution coming up. Is it coming earlier in the thinking process? It is coming later in the thinking process. What is happening over there? That is what they are trying to find out. And what they are saying is that for simpler problems, reasoning models often find the correct solution early in their thinking, but then continue explore incorrect solutions. That is what is happening over here. This phenomenon is referred to as overthinking in the literature, leads to waste of compute. For example, when I tried a simple problem like, what is the product of two numbers or something, it generates the correct solution early. But after that, it goes into, let me confirm this solution, let me do this, let me do that, lot of, thinking it does. So that is kind of overthinking which is seen, right? That is what they are saying over here. So as problem becomes moderately more complex, this trend reverses. Model first explore incorrect solution and later in thought, mostly later in thought, arrive at the correct ones. So when you have slightly complex problem, it does incorrect solutions first and then goes to, the correct ones, right? Finally, for problems with higher complexity, collapse emerges. It is not able to really solve the problem. So that is what they are saying over here. So this is some weird behavior from your large reasoning models, which they have observed over here in the data itself. Okay. So what they are saying is that if you have simpler complexity problems in the reasoning model solutions, when it is trying to generate the solution in its thoughts, you will see that first it gets the correct solution and then it tries incorrect solutions. Overthinking happens. But when complexity increases, you will see that it generates incorrect solutions first and then moves towards correct solutions later in the process. And after some time, it kind of collapses. That is what they are saying over here. Okay. Now, why does this behavior happen? That is what they are trying to, what is this puzzling behavior of reasoning models? Okay. So what they are saying is that even if you provide a correct solution in the prompt saying Tower of Hanoi needs to be solved like this, still the algorithm still the large reasoning model fails to generate proper responses beyond a certain complexity. Okay, that is what they are saying over here. All right. So even if you provide a correct solution in the prompt, provide the algorithm in the prompt so that the model only needs to execute the prescribed steps, performance does not improve. So it is not really able to make use of the solution to generate, the algorithm to generate the solution. That is what they are saying over here. So what they are saying is that large language models, there are three distinct reasoning regimes in large reasoning models. Standard LLMs outperforms large reasoning models at low complexity. LRMs excel at moderate complexity, and both collapse at high complexity. Particularly concerning is the counterintuitive reduction in reasoning effort as problems approach critical complexity, suggesting an inherent compute scaling limit in large reasoning models. So large reasoning models are not going to take you to AGI. That is a simple conclusion over here. Okay. So detailed analysis of reasoning traces further exposed complexity dependent reasoning patterns from inefficient overthinking on simpler problems to complete failure on complex ones. These insights challenge prevailing assumptions that large reasoning model capabilities suggest that current approaches may be encountering fundamental barriers to generalizable reasoning. So with the current approach of large reasoning models, we may not be able to achieve generalizable reasoning. So this is what they are saying over here. Then they talk about their limitations, where they are saying that this is quite simplified. Okay, the puzzle environments may not, that help them get controlled experimentation, but they may represent a narrow slice of reasoning tasks and may not capture the diversity of real world or knowledge intensive reasoning problems. So further work needs to be done, right? That is what they are saying over here. But this is interesting, but this was something which was known, which we had seen in practice, that when you give a really complex problem, sometimes large reasoning models are not able to work. When you have a very simple problem, large reasoning models are an overkill. They go into this thinking loop, right? And for some problems, they work really well. So this is not like an unknown thing in this field, but it is good to see it being backed by some experimentation. But still, the timing of this paper seems a little bit circumspect, with Apple being a laggard in the AI space, their Apple Intelligence being a complete utter failure, right? So everything needs to be taken with a pinch of salt. I hope you like this video on the illusion of thinking or about limitations of large reasoning models, their strengths and weaknesses. Hope this video is useful. See you in another video.